Okay, welcome back. Now that we've discussed one method of memory reclamation, transparent page sharing, let's take a look at the other ones. The other ones that actually are as a result of there being a shortage of memory. That's the one thing about transparent page sharing, was that it's something that if it ever happened, it was happening all the time, as the nature of how the system could be efficient and how it actually mapped memory pages on a system. Whereas these other memory reclamation techniques are due to the fact that the system is running short of memory. And they basically happen as memory becomes less and less available, right? As it becomes more and more scarce, then the level of aggressiveness is going to be determined by the system. So the system starts off with what we like to call the least negative of the memory reclamation techniques, right? So there's some negative aspect to this, but it's the least negative of these memory reclamation techniques, right? Transparent page sharing was completely transparent, so that there is no negative impact in this sense. But with the memory reclamation techniques that we list here, these involve some form of paging. We could do paging in the guest, we could do paging at the host, and we can do other things. So what do we have here? Well, the first one is this mechanism called memory ballooning, right? This happens in the guest OS. This is actually something that happens as it occurs because the installation of VMware tools installs this thing called the VM memctl. This is a driver that sits in the guest OS that allows the VM kernel to communicate with this driver to tell it to do work for us, right? To have it do work for the VM kernel. And basically what happens, the ESX server starts realizing it's running low on memory. It's going to start looking at where are the best VMs on that system that could cause their own memory systems to page out their own idle memory. Basically, what this is looking for, the whole ballooning mechanism, is looking for which VMs have the most idle memory, because if we could let the guest page that out, the guest won't actually miss those pages at all because the guest wasn't using them, right? Or the user wasn't using them. Because you remember, a VM may have a whole set of memory that's been allocated, but maybe not all of it is actually active. A whole set of it could be inactive. And remember, that's also one of the things that the VM kernel checks. What's the state of the memory pages that have been mapped at the VM kernel level? They're either active or they're inactive. So the VMs who have the greatest idle memory are the greatest candidates to have their memory paged out. But instead of the VM kernel figuring out what to page out, why not let the guest figure it out? So that's what happens. Say, for instance, a VM has 1 gigabyte of memory, but the VM kernel has determined that VM has 400 megabytes of idle memory. We can actually let that guest free that memory up, and then we use the balloon driver to also inform the VM kernel when that's actually happened. So what happens? The VM kernel informs the balloon driver it needs to find 400 megabytes for the VM kernel. The balloon driver essentially will start pinning memory, reserving memory in the guest OS. The guest OS has to make room for this 400 megabyte thing, and so the guest is going to start paging out the memory that it doesn't need at this point in time. It's going to basically free up memory that isn't used, that's basically been moved off the free list or been moved onto the free list, and then we can basically take that and give it back to the VM kernel. And we could also have the balloon driver will also force the guest to page out idle memory. And that's what's going to get swapped out into the guest, right? Any idle memory that's still tied to applications. And once that's happened, the balloon driver can inform the VM kernel that it was able to free up 400 megabytes, and the VM kernel can now grant that memory to another VM who is actively using their memory. Once this memory shortage is over, then the balloon driver can then start releasing the pages, where the guest can then start paging it back in when it needs to. So the goal of the balloon driver is to basically find the free memory and the idle memory, focus on that, get the idle memory paged out in the guest, the free memory gets moved off onto the free list and taken out of the VM kernel space, and basically try not to touch any VM active memory. That would be more problematic, right? Because then that would be something that an application was using. The goal of the balloon driver is to be gentle, find the memory that nobody was using. It had allocated, but it just wasn't using for some time. That would be a good candidates to get placed on disk. Now, there is a threshold here of how much can the balloon driver actually balloon up to. It's 65% of your VM's configured memory. So the goal here, again, is to prevent the balloon driver from consuming active memory from that guest. So The assumption being that the VM will typically need at least 35% of its memory. So that's the part that the Balloon driver can't touch. That's a tunable parameter that is not recommended to be changed. It's something that you'd have to set in the VMX file. Instead, if you do want to adjust what the Balloon driver could claim or not claim, what you can do instead is actually set a VM memory reservation. When you set that, that's going to guarantee what portion of a VM's memory could never be paged out, even by the Balloon driver. Now, other things can happen when you have the Balloon driver doing its thing. Its goal is to bring the system back to a healthy amount of free memory. But if the Balloon driver is not sufficient in finding a free amount of memory to bring this ESX server's amount of free memory to a healthy amount, then the system may go to another more significant level of memory reclamation. The next stage is what's called compression. At this point, what the VM kernel will do is it will find the pages that belong to the VM, and wherever it can, take the 4K byte-sized pages and compress them down to 2K, or even better, compress them down to 1K. Whatever pages it can will actually be compressed into what's called a compression cache. Every VM has a designated area of its configured memory for this compression cache purpose. That, by the way, can grow and shrink based on what's going on in the system. And then if it turns out that the page that was compressed turned out to be something that the VM needed, well, then the system simply decompresses that page and then will compress a different page instead. And so this saves a lot of I/O resources because there isn't any disk I/O involved with this at all, right? This is simply moving memory from a 4K page to a 2K or 1K page. This is all working at CPU and memory speeds. It's very fast and very efficient. And if it turns out that this was not sufficient, then it goes to the next extreme, which is the swapping stage. And in fact, the pages that are in the compression cache are the first pages to be sent out to the swap area. They'll be actually decompressed to 4K again and then sent out to the swap area. So swapping is now where all bets are off, right? Now the system is not concerned whether the page is free or idle or active. When the host is at the point of swapping, it's at its own point of last resort. It's not going to do anything else except for focus on getting the amount of memory that the host needs in order for self-preservation. So every VM is a candidate to have their memory sent out to the swap file, regardless if it's free, idle, or memory. So if you ever see this, you know that the system is completely out of memory. And that's the thing, you can kind of get an idea of how serious the issue is with memory on your server by looking to see, is the system ballooning, or is it compressing, or is it swapping, right? And the further down that list is how much more severely limited the amount of memory is on your system. Of course, you don't want to see any of this, right? Ballooning is your warning sign, right? That's your early warning sign that you need to take care of an issue. If it's now turned into compression, now it's getting more serious. And if it's now swapping, now the system is severely short on the amount of free memory. So that's the other set of the reclamation techniques. And again, they are done in that significant order. So let's just review what are the different types of memory reclamation techniques that we have out there. Well, there's one method that's where we request memory from a guest operating system, right? We know that that's actually ballooning. Then what shares identical memory pages between virtual machines? Well, that is actually transparent page sharing. That is disabled by default. We actually only do intra-VM page sharing as a default. You can enable inter-VM page sharing with those two different settings, right? The host setting and the VM setting. Then let's see here. What swaps a virtual machine's memory to a flash device? Well, that's the host swap cache. If you've got the disk installed, you'd have to actually do this on every single one of your ESX servers and then configure that as the host swap cache to basically circumvent the additional latency involved in having to write to the swap file. Number 4 says places a virtual machine's memory in a swap file. Well, guess what? That is the host level swapping. And then finally, compresses the virtual machine virtual pages and stores them into memory. Well, compresses. Well, we know already by process of elimination, it can only be compression over here, but also by the name of the hint, it pretty much tells us that's what that is. So I think we got all those right. Okay, very good. We've now finished this discussion on memory reclamation techniques. Now let's take a look at, after the break, when does it do all these different things, right? When does it do ballooning? When does it do compression? When does it do swapping? Well, we can actually find out through formulas when would the ESX server do each one of these different memory reclamation techniques. So we'll take a quick break and we'll see you in a few minutes.